Swayam Prabha. Digital India. Educated India.
Welcome back. In the last class, we started our discussion on the IP address lookup, what all we can do to do the fast IP address lookup, given that the network routers have to function very fastly and need to handle the packets with the several gigabits speed. So this is the diagram that we saw in the last class. There are three routers and some computers connected to each other, and the router number, every router in fact has got a routing table, and here is a router which has got router number 2 has got this routing table, so which has got the destination IP address and the corresponding port number on which the packets have to be forwarded. So if this router receives a packet, let's say this router receives a packet with the destination IP address 20.0.1, it means that it need to forward it to a packet in port number 3. Now we saw one data structure in the last class, which is the binary trie. One example, we saw how to construct the binary tree given the prefixes, IP address prefixes. So let's now continue that discussion. We'll try to build some more. The agenda for today is we'll try to look at the variants of the binary trie data structures. First we will again take an example of the binary trie, and then look at what are the performance issues, what we can do probably to improve the performance further, and then look at different variants of those data structures. So here is a set of prefixes. There are 9 of them on the screen, P1 to P9, and the prefix binary digits are actually shown. So let's try to construct a binary trie for these set of the prefixes. So as usual, P1 is a star, then I need to start with the root node, and then that's the my prefix P1, and P2 is saying 1 star. I go to the right and have a node here. This is my P2, and P3 saying 0 star, so I need to come to the left and 2 nodes. This is my P3, and P4 is 1 0 1. So 1 on a 1 I already have this, on a 0 0, and this P4 is 1 0 1, 1 is already there, and then I go to the left with the have a node on 0 and then on 1 star. So I go to the right, this is my P4, and P5 is 111, 1 is already taken care. So a node here, this is my okay, 1 2 ones and then followed by a third one. This is my P5, and P6 is 1 followed by 3 zeros. 1 followed by 1 0 is already there, and a second 0, there is a node here, and then on the third 0 there is a node here. So this is on 0, and this is my P6. Okay, and P7 is 111 followed by 0 1. 111 is already there, followed by a 0, a node here, and then an 1. So I come here, this is my P6, and 111, and P8 is 111 followed by 00 followed by 1. This 1 0 is already there, 1 node, and then followed by a 1. You are here, this is my P8. P9 is 1 followed by 4 times 0 followed by 11 star. So 1 followed by 3 0 is already there, 1 more time 0, this is the node, and then a 1 and then a second one. This is my P9, and I need to mark the nodes which are corresponding to prefix like that I do it using the blue color here, and this is my P4. Similarly, P5, P7, and then P8, P9, and basics. So that's the binary trie for these set of the prefixes. Given these 9 prefixes, these are the this is how you construct the binary trie. So little bit about the ones. So how many times depend the height of the trie can be depending on the length of the prefix. So here the length is the P9 has got this and 1 4 times 0 followed by 11. So that will correspond to the longest length prefix in this trie structure. So you require those many number of the pointer access in this trie to validate any of the or to find out what is the next stop router for the routing when you make the routing decisions. Yeah, so the prefix examples that we saw in the previous case, whatever the examples we talk are all in this format, maybe 0 0 star, 1 0 star, something like this, or star or something like that. But in real is the prefixes might be expressed in a different way. So maybe for example, if you take the CIDR case, the prefixes are in this format. Let's say I have 10.0.0.1/1. What it means is you convert this thing into binary 10.0.0.1. So 10, if you convert it to binary, you will have 0 0 0 and then 1 0 1 0, and the second this will have 0 0 0 4 6 8 times zeros and followed by another 8 times zeros and followed by 1. So you take the first bit only, the network portion is actually only the 1 bit because /1 is there. So the prefix corresponding to this expression is 0 followed by irrespective of whatever is there, I don't care. So 0 star is the prefix corresponding to this CIDR notation. So similarly, I might have something else as well. So let's say I have 192.10.10.10/2. What it means is, again you convert 192 into binary, 10 into binary, concatenate all the binary numbers and pick the initial 2 bits of this binary number, and that will be you prefix that. So let's say it turns out to be 10. So 10 star would be the prefix corresponding to this number. So this is not the exact 10 star, is just the canonical example that I am giving. So that is how, given the CIDR notation, you can convert that into binary prefixes of this format, and then subsequently you can construct the binary trie for that prefix. So there might be some examples corresponding to this in the tutorial and later exercise sections. You can take them, take a look at that. So now let's take a deep look at the performance of the binary trie. How does actually, what is the space complexity, what is the number of the lookups I need to do. If I have to do the update operation, then how much effort I need to put. So in asymptotic format, we take a look at that. And before that, maybe you can take, if the given this is how the binary trie is constructed, what is the structure of the node, what is the data structure, actual physical data structure that I am going to build in terms of the software implementation. So this is a simple binary trie is a simple binary tree. So where you can have 2 nodes and 2 childs and then the node value. So I can have a linked list kind of the data structure used for this one. So and the node constituents can be the following. So one is you got the indication of whether this particular node is a kind representing a prefix or it is not representing a prefix. So for example, if I have this one, this is my star, this is the prefix P1, and then I might have 0 followed by 0, this is 0 0, and this node is actually representing prefix P2. But this node is not representing, the middle node is not representing any of the prefixes. So I can have an indicator variable as to indicate whether this is representing a prefix or not, and then so each node can have two childs. So we will have two pointers, one the left pointer and the second one is the right pointer. So two pointers. So every node can have this kind of the structure, and you need to create those many number of the structure variables as there are number of the nodes in the binary trie. So if there are n number of the nodes in the so n times the whatever the space this is occupying, that would be the space required for the entire trie. And the space requirement is n times the one of the w is the width. W is width means the prefix which is the of the longest length. So remember the prefixes are order in this increasing format. So here the P9 has got the high length, and n here is the 9 times the whatever the width, here it is 7. So 7 times the 9 is the total space required for entire binary trie. Since this is the asymptotic notation, so the maximum that we have is the one that we take, so that is the bound, and that is space requirement. If I have to do the lookup operation, so given that if we are given a binary trie, that structure, and then in the real time when the router receives a packet, you pick up the destination IP address from the header of the packet, and then against the data structure that you have got, whatever binary trie you have built, you will going to evaluate that what is the best match for this particular destination IP address. So that would take those many number of the lookup operations, as many what is the width of the or the longest prefix that I have in the prefix table. And if I have to do the update, so let us say today I got these 9 prefixes, but as the more number of the computers get connected to the network, the number of the prefixes in the table would increase, and if I have to do an update operation, then what is the cost of that? That would again take the update operation, also take the order of the w is the width of the longest prefix. We discuss routers have to do many number of the packet forwarding decisions, so millions of packets per second, and for one forwarding one packet you need to do these many number of the memory references. How many? What is the width of the longest length prefix in my table? So what could be the longest length that I can have in the binary trie? So if you take the case of the IP version 4, there are possibly you can have the width as 32. So the height of the tree would be 32, and then in the worst case for forwarding one packet I need to do 32 number of the memory references, the pointer references from one node to another node. Either you take the left child or the right child and then keep traversing that. Those many number of the memory references. So that is actually kind of the slow, in the worst case 32 references. And second thing is what could be the size, total size of this binary tree, binary trie. In the worst case it can be a full tree and full binary tree. So it can have the leap 2 to the power of 32, all possible IP addresses might be listed on the binary trie, those many number of prefixes. Particularly you do not have any room for every possible IP address is there in your table. So although that is theoretical, but that is the when we talk about the data structure, that is the possibility that you have got. Now the question that we ask is, instead of doing 32 number of the pointer references or traversing the trie, that is the worst case, can we do little better in terms of the memory references? So remember the memory references traversing the pointers going there would take the time. Can I do some optimization? So now what we do is we will try to look at some of the optimization that is possible. Basically, I do not want to do 32 number of the memory references or pointer traversals for one IP address lookup. can I do something better? Maybe reduce some of the unwanted nodes in the structure and then try to reduce the height of the tree. If you reduce the height of the tree, the number of the pointer references would also reduce. So, let us go back to the previous example here that we as what we notice is some of the internal nodes. So, for example, if I take the case of this left subtree which is here, from P1 to P3, from root node to this node, there are two bits, one 0 followed by 0. The intermediate node that is here is not playing, it is not representing any of the prefixes. So, can I get rid of this intermediate node so that I can bring reduce the possibly the height of the tree. Here in this case, if I do only this compression, the height is not reducing, but if I apply the same rule across the all paths that exist in this binary tree, then you possibly reduce the height of the tree. So, let us try to understand one variant of such optimization that is possible, which doing is called as the path compressed trie. So, what I am trying to do here is the path that exists from the root node to any of the leaf nodes, if any of the intermediate nodes have got a single child and it is not representing any of the prefix, that I am going to get rid of. So, here is a simple example. So, I start the node here. So, 0 followed by a 1, and this is my P1 and this is my P2. What I want to do is convert this into, this is the, this trie has got height of 2. So, I want to convert this into this format. So, this is my P1 and then 0 followed by 1. So, I this 0 and then make this node as the prefix P2, and then I need to remember this entire thing is actually skipped. What is how many number of the bits that I have skipped, and the second thing is what is the bit, what are the bits that are skipped. In this case, that I am going to remember. So, that is going to be indicated with the two variables inside this. One is called as the skip length. So, here is case I am going to write it as 1 because I skipped one bit, and what is the segment that is skipped in this case. So, it might be the left child or the right child. Here in this case is the right child. So, I am going to remember that the segment that is skipped is 1. So, it is not necessary that only one is skipped, it might be more than that. So, for example, this is the one example. So, if I have a trie which is in this format, a 0, 1 and then a 0 and then a 1. So, this is my P2, this is example number 1, this is the example number 2, and when I do this version, what I want to do is to get this. So, this is my prefix P1 and then I retain this node and make this node as representing P2, and here is case again with the variable value. What is that? The skip length, here is the 2, I skipped 2 bits, and then the segment that I skipped is 0 followed by 1. So, I am going to remember this. So, how does this actually help? So, when I am trying to match the prefixes given the packet arriving at a router, I pick up the destination IP address from that header and then try to match with this. Right. So, what then if my prefix is let us say this destination IP address is 4 bits, it is 0 followed by 1 followed by 0 followed by 0. So, what I am going to do now is pick up this try. So, 0 is matched, I come here and then 1 is there, but the segment is saying 0 followed by 1, that does not match. The best previous prefix that is matched is the P1, that is the default way you forward it. On the other hand, if you have a 0 followed by a 0 followed by a 1 followed by a 0, this is the destination IP address. So, I pick up the first bit here and then match here. Okay, you come to the node P2 and it says that the skip length is 2 and the segment that is skipped is 0 1. I match 0 followed by 1 at the node P2 and that matches, and the prefix, this is the node which is actually indicating the prefix because we have highlighted. So irrespective of what is there in the third, fourth or the subsequent fields, I am going to say that so far whatever the best match that I got is the P2. That is how actually it is evaluated. In effect, what I am trying to do is, at the expense of storing some more content in the node, I am trying to minimize the number of the memory references, the pointer references that I have got in the table. So, this is possible if you have a processor inside the router which is capable of doing multiple number of the bit comparisons in one go. So, let us say my processor has got an instruction. When I say the processor, it is the processor sitting on the router, because you need to do some computation, you need to install this routing table on that router, and then I am building a data structure, picking up the destination IP address from the packet and then doing the comparison. That hardware that exists on the router is capable of doing this, and if that hardware it is able to do multiple bit comparisons, then I can squeeze this and build a compressed data structure which has got the reduced height comparable to the binary trie that we discussed. So, let us take some of the examples and then see what is the advantage that we get by doing this, how many number of the memory references we can reduce, whether the asymptotically is it going to offer any benefits or not. We will try to find out in a minute. So, let us say I got these prefixes. So, let us say P1 is the prefix which is a star, and P2 is the prefix which is getting 0 0 star, and P3 is a prefix which is representing 1 1 star, and P4 is a prefix which is representing 1 1 1 1 0 star, and P5 is the prefix which is representing 1 1 0 0 star. I got 5 prefixes, and then let me try to construct the path compressed trie for this set of the prefixes. So, before we do that, let us construct the traditional binary trie and then look at the height of the binary trie and compare to that what is the height of the path compressed tree, and then we will be able to appreciate what advantage that it is bringing. So, as usual, I start with the root node, and then that is my prefix P1, and then it says it has got the 2 zeros. I come to the left, this is my P2, and P3 is 1 1 star. I go to the right, this is 1 1 followed by the second one, this is my P3, and then P4 is 4 times 1 followed by 0, 2 times 1 is already there, and the third one and the fourth one, and then 0, this is my P4, and P5 is 3 times 1 followed by 2 0, 3 times 1 is here, and then I take a branch here, go to this node, 1 0 followed by the second 0, my node, this is my P5. So, let me change the color of this one, highlight the prefixes. So, this is the prefix P1, prefix P2, prefix P3, prefix P4 and prefix P5. That's it. So, let me again construct the this is the binary trie, and the path compressed trie for these set of the prefixes looks something like this. So, I take this as the input. As usual, I start with the root node. This is my P1, the default prefix, and then any node which is intermediate and having a single child, that would be eliminated. So, if you have multiple of them in sequence, then you eliminate all of them in one go, and remember what is the skip length and what is the segment that you have skipped. So, in this case, if I go to the left, I am going to retain this 0, this and then make this as my P2, and I am going to say that the skip length here is 1 and the segment that is skipped is 0. And I come to the right and So on this particular path, this node which is intermediate between P1 and P3 can be eliminated. The same logic, I retain one and then say mark this as my P3, and what I skipped here is of length 1 and the segment that is skipped is 1. And similarly, the next node has got 2 childs. This node, nothing we can do about it, just keep it as it is. But on the path from this node to the P5, I got an intermediate node. This can be removed. Similarly, this can be removed. So I am going to retain a will path and then make this as P5, and the skip length is 1 and the segment that I skipped is 0. And similarly, I am going to retain this label and make this as my P4, and the skip length is 1 and the segment that I skipped is a 0 segment. And then again I need to highlight these nodes with the what representing, whether they are representing the prefixes. This is representing a prefix, highlight this. This is representing a prefix, so does this one and this one and then this one. So you can now compare. This has got the height of 1, 2, 3, 4 and 5. That is the height. 5 is the height of this binary trie, and from that we got a structure which is 1, 2 and 3. So just having the height of the 3. So 2 pointer references we got rid of, and then that reduces the height of the tree, and then you are able to do the comparison with the minimal number of the at minimal in the sense that is the best that we can do, at least using this structure. You will be able to do the decision where to forward that packet, on which port number you will be able to find out. So that is how you construct, you optimize by having something in the nodes, extra things by remembering what I skipped and how many number of the bits I skipped, these two quantities. Then I am able to reduce the height of the trie, and thereby the number of the memory references. Remember, you need to concatenate what is the label on this path between the node and the next its child, and then what is the segment that it is indicating. Then you do the comparison in one go. So let us try to take one more example and then construct the path compressed tree before we actually look at the asymptotic performance of this optimized tree structure. So here is, so my P1 is as usual the star, P2 is 1 star, and P3 is 0 0 star, and P4 is 1 0 1 star, P5 is 1 1 1 star, P6 is 1 0 0 star, P7 is 1 1 0 1 star, and P8 is 1 1 1 0 0 1 star, and P9 is 1 0 0 0 0 1 star. So as usual, construct the path compressed binary trie for this example. So as usual, we will first try to do the binary trie. So this is my P1 and 1 star, this is my P2, and 0 0 star, that is one on the left, and on the left this is my P3, and P4 is 1 0 1. So 1 already we have, and the 0 you come here, and then in 1 you go to the right, that is your P4. P5 is 1 1 1. So on the right and one on the right, this is my P5, and P6 is 1 followed by 0 0, 1 followed by 0 is there, you take child, and then the one, this is my P5, P6, P7 is 111 followed by 01. So 0 and then 1. This is my P7. P8 is 111 followed by 001. So this is 0 and then 1. This is P8, 111 followed by 00 followed by 1. And P9 is 1 followed by 4 times 0. 3 times 0 is this touch and then followed by a 0 and then 11. This is your P9. So what is the height of this trie? 1, 2, 3, 4, 5, 6, 7. 7 is the trie, and I need to, as usual, mark the nodes which are representing the prefix with the blue color. Let me do that. And this node, this one. Okay, yeah. And again, let's try to construct the path compressed trie for this one. This is, well, let me do it here. And as usually, if I take this path, then I can get rid of one unit node. This is my P3, this is my P1, and the skip value is 1 and the segment that is skipped is a 0. And on the right hand side you have a 1, and then so this node has got the 2 childs. I cannot do anything about it, just to retain them as it is, 1 on 0 and on 1. And take this, this has also got the 2 childs, 1 on 0 and another one on 1. So retain that as it is. This is P4, and this path. So peak 6 can be, this node can be got rid of, and then the peak 6 can move towards. So this is 0, and then this node is the P6. So what I skipped, 1 0, that I am going to remember here. Skip is equal to 1 and the segment that is skipped is 0, and then followed by P9. Then I have a 0 here and a node here. This is my P9, and I am going to write the skip length is what all I skipped. This and this is 2, and then the segment that is skipped is 1 followed by 1. So 1 followed by 3 zeros and followed by 2 zeros, 1 0 and followed by 1 which is there, that is your P9. And similarly this is done. So on the right hand side the P5 can move, what this can become your P5, and then the segment that is skipped is a 1 and the skip value is also 1, and this is your P5. And then on the left hand side you have this node, it has got 2 childs, you cannot do anything about it, retain them. This is going to be your P7, and this one has got one intermediate node which is having a single child, that can be removed. So you got a 0, and this will become your P8, and you remember what you skipped. Skip length is equal to 1 and the segment that is skipped is also 1. So that is how, this is the trie corresponding to the binary trie that is being here. So from the height of 7 we came to the height of 1, 2, 3, 4 and 5. So we could reduce the height of the tree by length of 2. Using 5 memory references, you are able to actually do the traversal of this trie and then making the decision on where to forward the packet to. So that is how you optimize the trie. And if given this thing, what is the performance benefit that you get of this? And before we actually take a look at that, let's try to bring what is the, because now we are remembering introduced couple of more variables inside the node. Earlier it was only indicating whether the node is actually representing a prefix or not, and then the left and the right child in the binary trie. But now we have a couple of more variables. The node structure has got changed. So one is the indicator which was there is as it is there. So whether this node is actually representing a prefix or not. And the second thing that it has got is what things, the skip length that we introduced, that is one part of the array, and then we are also remembering what is the segment that is kept. So the sequence of binary digits, so whether it is 0 1 0 1 whatever it is. So and then it has got the two pointers as it is, one is the left pointer and second one is the right pointer. So now the node, each node has got the more space. Now you need to tell whether the, it can skip length can be 0 as well. Every node has got a skip length. If it is 0, whatever is the skip length, those many number of the bits should the segment portion should have, and then the left and the right child as usual also having. So at the expense of some space at each node, we are able to compress the height of the binary tree, and by reducing the number of the pointer traversal, we are able to make the decision. So now asymptotically, if I have to how much space it requires, order of n, where n is the number of the prefixes you have got, only those many nodes probably I can have, if provided you are able to reduce the height of the trie significantly. So meaning you will have many intermediate nodes which are having the single child, which apparently if your routing table is very sparse and is one very less number of the entries are there, it is possible to have such a structure. And if that is the case, theoretically, although this is not exact thing, you will have an order of n number of the elements in the, it requires that much space, and otherwise you will fall back to the, in the worst case you will fall back to the order of n cross w. So that is the binary trie. So when does this happen? If the binary trie is full trie. So for example, if this is the structure 0 the node, and every node has got 2 childs, then you cannot do any elimination. So remember, elimination will happen only when the intermediate nodes have got the single childs that can be removed. So if you have 2 childs, then the elimination is not possible. So if your trie is having this kind of the structure, it is full, then you cannot do any elimination. In that case, the, in fact it takes more space because you have introduced the couple of more variables inside the node structure, it will take more space. No optimization is actually possible. But given the practical how the routing tables look like, the prefixes look like, the reduction, height reduction is indeed possible in the, this is basically researchers found out using looking at the practical routing table, how they look like, and how much space is actually binary tries taking. Can we get some optimization using the practical we found routing tables? They came up with this kind of the optimization. And the lookup in the worst case still takes the order of w, where w is the width of the longest prefix that you have in the routing table, and the update time is still takes the order of the w time. When the new prefix is just the extension of the longest prefix that we have. So currently, let's say in the previous case I have height of the 7 is the prefix length, and then the new prefix that you get is just an extension of these 7 bits. Then you will have to traverse those 7 bits first, 7 references, and then you add the new node into the trie structure. Again, this is in the worst case when the height of the binary trie, that path compressed trie you constructed do not have the optimization possible, and then the height of the trie is w, and then the extension is going to take the first as you traverse w bits, and then the new addition can be done. So that is the one optimization that you can do on the binary trie. And remember what is that we did here? instead of matching one bit at a time, I am trying to match multiple bits at a time. So, whatever the segment that we indicated here, those bits concatenated with the label that exists from the previous node to the child node, you concatenate these two and then you try to match in one go.